So a solution is something that's dissolved in water. At least any aqueous solution is dissolved in water. We know that. We know that when things are dissolved in water, if they are dissolving in water, they dissociate into their different parts. A lot of the time, it's ions. Normally, we get things that are either neutral, acidic, or basic. And so we have this whole class of chemistry called acid and base chemistry. We don't talk about the neutral part of it, but that's part of it as well. So, way back in the day when scientists were scientists because they classified things, not because they were doing actual experimentation, they classified different solutions in one of two categories. They went, that's sour. That's going to be an acid. And, oh, that's bitter. So that's a base.
They died trying to taste them.
Excellent question. Yeah, definitely something we wouldn't want to do nowadays, especially since we're dealing with nitric acid and hydrochloric acid and all of those wonderful things that we deal with on a pretty common basis here. They also said bases were slippery. So they tasted bitter and they were slippery. A lot of soap is basic in nature. So if we take a bar of soap and dissolve some of it in water, and we taste it, it's kind of an icky taste. But it's the bitter taste that they're talking about. And we know that soap gets kind of slippery. Well, with time, scientists were able to actually become more like scientists, and rather than just classifying things based on taste, they're like, well, let's get a little more scientific about it. So they said, well, if we look at concentrations, we can look at the logarithmic scale and calculate a pH value. We're going to do more of that at the end of this unit. But if the pH is less than 7, it's an acid. If it is more than 7, it is a base. What if it is 7? Neutral. Perfect. So some common examples of acids: orange juice, lemons, vinegar, that's our acetic acid, also known as ethanoic acid. Soda pop has a lot of carbonic acid in it. Stomach acid has hydrochloric acid as its main component. Bases, a lot of cleaners are basic.
Is it true that I heard somewhere that if stomach acid got on your skin, it would burn it?
I would think possibly. Because I know if hydrochloric acid gets on your skin, it would. But I'm not sure quite the pH of that, how concentrated it is. Let's not try it. So cleaners a lot of the time are basic. However, more and more cleaners are coming out that are acidic because different types of messes need different types of chemicals. So cleaners in the general sense, sometimes basic, but also sometimes acidic. Ammonia, however, which we know from the Haber process, is used in cleaning, it's used in fertilizers, it's used in bomb making. We know all of that already. Ammonia is definitely basic. Even though it's a cleaner, we're not lumping it in with the cleaners. We're saying ammonia is always basic. Baking soda we've used many a time, especially during those titrations when we spilled acids on the table. Sprinkle some baking soda on it. Often see a little bit of fizzling. Neutralizes it, because bases neutralize acids. And then soaps, again, back when science started, were all made the same way, and so we're basically bases. As time has evolved, and we're going to see this when we look at the pH of Hair Lab, some of them are not so basic anymore. So looking at different types of things like conditioner versus shampoo versus your face wash versus somebody else's face wash might give you some different levels of pH. What questions do you have so far? Okay, so we start out in history with let's classify based off taste. Realized soon that that wasn't so smart. So we actually started coming out with some actual scientific thought about what was going on the particle level. And Arrhenius here was the first one to come up with our first definitions of what an acid and a base is. And what he said was that an acid is something that contains hydrogen. It ionizes in water, to release a proton. So he is saying H1 plus is a proton. Why would that be? What was that? Yeah, it lost an electron, absolutely. What else is in the nucleus with a proton in hydrogen? In the most common isotope of hydrogen. Anything? Is there a neutron? Look at the mass. That's the average mass. Yeah, no, normally there is no neutron. So in the nucleus, I just have this one sad little proton. Somewhere flitting about it is an electron. But this 1 plus means that I lost that 1 electron. It's gone off somewhere else. All I'm left with is a proton in the universe flying around. So that is why the H plus cation is called a proton, because all that's left is that proton. So he said that acids contain hydrogen and ionize in water to release that proton. We're going to look at 3 different ones. And the reason we're looking at 3 different ones is because we call them slightly different things. So, first of all, hydrochloric acid. What is the charge of chlorine? Yeah, 1 negative. So, we know hydrogen is always a 1 positive. Chlorine here is a 1 negative, so hydrochloric acid is just HCl. It's dissolved in water to form ions, so we're going to say that it's AQ, aqueous, and it dissociates into its different ions, H1 plus Cl, 1 negative. Sulfuric acid comes from hydrogen reacting with the sulfate ion. Go ahead, show me with your fingers what the charge, don't worry about the negative part, of the sulfate ion is. It's one of our polyatomics. It's SO4. Excellent, I'm seeing a lot of 2s. Yes, it's SO4 2 negative, so we have H2 SO4 for our sulfuric acid. AQ, aqueous. It's going to dissociate. If it dissociates completely, it will go into the H1 plus, and there's going to be 2 of them, so we put a coefficient of 2, plus SO4 2 negative. The first one that we dealt with is often called a monoprotic acid. Mono for 1, protic for proton. So it released 1 proton into the solution. H2SO4 released 2 protons into the solution. So we call that diprotic. It releases 2 protons. Okay, show me with your fingers the charge of the phosphate ion. Good, I see some of you that aren't quite sure what the charge is, but you're looking at the pattern that we have going on here. Yeah, it's 3, so it's PO4, 3 negative, reacting with a hydrogen, which is a 1 positive, gives me H3, PO4. Aqueous. How many hydrogens is it going to give me when it dissociates?
3.
Yeah, 3 hydrogen ions, or 3 protons, plus SO4, PO4, 3 negative. So we call this one a triprotic acid. Yeah, Mohammed. Not necessarily. We're going to talk about strength in a while here, in a couple of days. Good question. Glad you are thinking ahead. Okay. Well, he talked about acids here. That's not all that we talk about when we talk about this type of science. What else do we have to talk about? Bases, absolutely. So Arrhenius had some comments to make about bases as well. He said that bases contain an OH, hydroxide, and that it ionizes in water to release a hydroxide ion, OH1 negative. So we could look at potassium hydroxide. The charge of potassium, since it is an alkali metal, is a 1+. Hydroxide is always a 1-. So we have KOH, aqueous, dissociates, forms ions of K1+ plus OH 1-. Pretty cool, huh? Seems like a pretty smart guy. Can you think of any bases that do not have an OH? We wrote it down before. Go ahead. Ammonia, absolutely. So, this theory works all fine and good, except when we deal with ammonia. We know that that's a base, but it doesn't fit this definition. So this is a fine working definition for us, but we need to delve deeper. We need to find something that goes through more of them in more general terms. So that is where two gentlemen working in different countries, working independently, came up with the same definition. So they're both stated as the people that discovered it, since they both did but weren't working together. Bronsted-Lowry acids, they said, are hydrogen or proton donors, and bases are proton acceptors. Acids are proton donors and bases are proton acceptors. So we're going to write our equations a little bit different for this one, and we're going to look first to see if this definition deals with that one that was tricky for us. So ammonia is NH3, and rather than writing aqueous this time, we want to actually look at what it's doing with the water when it's put in it. So we're going to do plus H2O. This is an equilibrium reaction, so we're going to do a forward and a backward arrow. Now we know ammonia is a base, so it's going to accept a proton from somewhere. Well, the only other thing here is the H2O, so one of these hydrogens is going to come over to the ammonia. It's going to form NH4 1+, the ammonium ion. And the leftover stuff of the H2O is just OH 1-. It's lost its proton. There's one less hydrogen there. Well, we can write down here that this is a base. The water then is acting as an acid. Since this is a reversible reaction, that means that the hydrogen has to go back to the OH to get back to the other side. So that means in this case, this NH4 1+ is donating a hydrogen. It's acting as an acid, but since it's on the product side, we're going to call it a conjugate acid. And the OH 1- is a conjugate base. And we see that the base is related to the conjugate acid, and the acid is related to the conjugate base. Yeah.
So you call something conjugate product.
Perfect, yeah. So let's define those two words, conjugate acid and conjugate base. A conjugate acid is formed by a base accepting a proton, and a conjugate base is formed by an acid donating a proton. Yeah.
So it's saying that what is an acid and what is a base is relative to what's going on.
On the other side, yep. Good.
Because water is,
In this case, an acid, but it could be a base. Absolutely. And that's called amphiprotic. It can act as both an acid and a base. Awesome. Thank you. Okay, I know some of you are still writing, but we're going to move on and get at least one more example done before you guys have to leave today. So, carbonic acid, that comes from the carbonate ion. CO3 2 negative. So that means our carbonic acid is H2CO3. Going to react it with some water. It's going to form an equilibrium reaction. We already know that this is an acid. So it is going to be a donor. It's going to donate one of its hydrogen to the water. The water then is a base because it is accepting that hydrogen from the H2CO3. So I'm going to have two products. One is now HCO3, 1 negative, that's not quite us yet, and the other is H3O, 1 positive. Sure. Okay, so going back the other direction, the H3O is going to be my conjugate acid, and the HCO3 is my conjugate base because it is accepting. So the acid related to the conjugate base, the base related to the conjugate acid. The HSO4 in the next example you can do at home. It can go both ways.